This is toSum number 4. Input is a binary search tree. LeetCode 653. So this is a variation of the very popular LeetCode challenge called toSum. This one is very interesting because this time around, we have a binary search tree, which is what you see here, this small graph. So we have 6 nodes, and this is not just any binary tree, meaning it's not just any tree where every node has a maximum of 2 child nodes, and they could be randomly positioned with random values. In this case, the position of every node and the value that they contain in this graph here has a meaning. So if you were to apply a depth-first search algorithm, for example, the in-order traversal algorithm, you would get 2, 3, 4, 5, 6, 7. And you see that now the numbers are in order, meaning that if we want to apply something like a binary search algorithm to quickly find a value inside of that tree, we could do so in logarithmic time. So this is indeed a BST, or a binary search tree. Now we have the root nodes of that tree, and we have a target number called k. So in this challenge, we need to return the value true if there exist 2 elements in the tree such that their sum is equal to the given targets. For example, these here are the values in the tree. Where they have null, it means that there is no child nodes. So here, for example, if you look at the roots, we have the roots, left child is 3, right child is 6. The left child of 3 is 2, the right child of 3 is 4. So far we have the values right here. Now 6 has no left child, that is why we have null in the array. It has a right child, which is 7, and 7 is here. Now inside of this array, which can be visualized through this BST, this tree here, what are the 2 values that can add up to k? There could be multiple values here. You see that we have 5 and 4 equals 9. We also have 3 and 6 equals 9. We also have 2 and 7 equals 9. And you get the idea. There could be many ways of summing up 2 different values to get the target k. Now, it depends on how you write your algorithm and how quickly you can find the sum. My approach would be very easy for you to understand, and hopefully you can optimize it. So this is another example, the same tree, but this time around, the value is 28, the target. So there is no 2 different integers that we can add up together to get 28, because the maximum or the largest 2 values inside of this tree here are 6 and 7. And if you add them up, you get 13. So there is no way we can get 28, and that's why we have to return false. In my solution here, I've added a few things. Before I explain it, let's look at the constraints. The number of nodes in the tree are anywhere between 1 and 10,000. The values also range from negative 10,000 to positive 10,000. The root is guaranteed to be valid, but not necessarily the child nodes. Likewise, the targets can be anywhere between negative 100,000 and positive 100,000. So now in my solution here, let me just capture all this, and then I'm going to press Ctrl X just to get rid of everything. And let me see if I can just reset to the default code definition. So I'm going to click confirm here, and you see what this challenge looks like at the very beginning. They give you the structure of a tree node. So we have a struct, every node has a value, has a left and right child. This is a constructor where the left and right child are null pointers, and the value is default to 0. We also have this constructor where we can set the value for val, and here where we can set the value as well as the left and right child nodes. So we only have this Boolean method under public, meaning it's accessible anywhere in the program. Now let's compare with what I had. It looks like this. You see that I've added this private access modifier here, and I've added a couple of member variables. So I have a C++ map where the keys are going to be integers and the values are going to be Boolean values. And then I also have a counter to count the number of nodes that I have in my tree. And I have a Boolean variable called found. At first, I set it to false because we've not found anything yet. Now, I need to initialize my counter variable. In some tutorials, you will see some people do things like this. Personally, I don't like to initialize anything outside of a constructor. So what I do is I just add this custom constructor here for the solution because this is the class, and then I initialize my variable to 0. Back to the function that they gave us, it's this one, where we have a root node or a node pointer here, and then we have the target k. This here is my full implementation. I'm first checking if the value of found is true or not. If you glance at my algorithm here, you will notice that it is a recursive algorithm. The found variable here is a member variable of the class, so it does not get reset anytime we run this function. Whatever value is updated on it will reflect for the whole class. If we've not found anything, we've not found the sum for 2 integers that add up to k, we can continue with the rest of the algorithm. Otherwise, if we found it, we return true. Now, let's say we've not found it. We first check if whatever nodes we are processing in the tree is a valid node. If not, then we quickly return false because we don't have anything to process, so we don't have any 2 different integers. There's no integer to compare it with, so we just return false. Now, if we've not found the 2 integers and we have a valid root, so we are here now, I'm going to count that node, that 3 nodes, by incrementing my counter variable by 1. And then here I'm going to verify if I can update the value of my found variable, which is this one right here. So to do that, I'm going to check in my map. Can I find the value k minus the value of my current nodes? If yes, then it means this condition here will evaluate to true, in which case found will be equal to true. Otherwise, if I cannot find the other integer to which I need to add up my node's value to get k, then this find method here will reach past the end of my map, meaning that this here, what I've highlighted, will be equal to m.ends. So this here will evaluate to false, and found here will remain false. So whatever value found gets in this line of code, I'm going to proceed to my next line and add my current node's value to my map. Because the map is int and boolean, these are the pairs of values in my map. The keys are integers and the values are booleans. When I update my map, I can do it like this. The integer value of my current nodes is the key and the value is true. Now I need to run this logic on every node, so I will explore my tree towards the left and run the same logic, and explore my tree towards the right and also run the same logic. And how I end my logic here, the important part, is that I need to return the value of found and evaluate this condition. Meaning if I have more than 1 node and I found the value here, then these 2 different conditions will be true. And we need true and true for the return statement to return a true value. Now, in all cases, I always want to make sure that I have more than 1 node to evaluate. Otherwise, it defeats even the purpose here because it's called toSum. We need 2 integers. So definitely I need more than 1 node. So if I have a single node, it's already false. You guys can just pause the video and read my code again. But for now, let us try and clear this here and use example test cases, which are these ones here. We have 2 of them. So let's run this algorithm, and we've passed both test cases. So now we can just submit the whole thing. We've passed all the test cases. So let's look at the details, how many test cases we had. 422, and we've passed all of them, which is not bad. The speed, I'm going to leave it as is. Of course, you can optimize this algorithm. For example, even in here, you could use a faster map, like an unordered map. I'm not sure if it's going to work here, but let me try it. Now I've changed this to unordered map. It still works. So when I click on submit now, we have an even faster algorithm. And this one takes about half the time. So now we are faster than almost 88% of all the submissions. So these are the sort of small tweaks you can do to your algorithms to speed them up. So let's look at the details again and see where we are faring in terms of performance. And we are here among the top performances. So that's not bad. If you guys like my C++ solution, you like my way of explaining, and you want more coding interview practice, please subscribe to my channel, and I'll catch you next time.